Hello guys, it's the Caribbean Bookworm, and in this final video for 2022, I will be giving you guys a very fun, you can say, like astronomy video that looks into the purpose behind taking some of those pretty pictures which you might have seen from various sources like NASA, ESA, or like the James Webb Telescope or the Hubble Telescope, etc. And these images are gorgeous. They show us the beauty and wonders of the cosmos in all its glory with different like cosmic objects. But I want to convince you that these images are not plainly like for aesthetic. They have scientific use, and the physics and the science behind them is actually much more fascinating than you would even imagine. Now, if you are like someone into astrophotography or you're a die-hard astronomy fan, you might have seen videos that say that, oh, those gorgeous pictures are not in reality like what you would see when you get a like picture, like an actual image of that same celestial object. Now, those videos, well, they're very much correct. There are a lot of videos explaining this concept, but I want to give my spin on this. So basically, indeed, if you grab, let's say, a telescope and you go outside for a stargazing session and you try to find, for example, one of those deep sky objects like the Orion Nebula in the Orion constellation. This is a gorgeous nebula. You probably have seen images of it before, but what it will actually look like is less like the gorgeous images which you've seen and more like something like this, like a black and white, like weird like blob. But this black and white thing actually can be like synthesized into the gorgeous thing which you've seen before, and this is done by some very clever techniques with filtering. And before I dive into that, let's try jumping into a little bit of the justification as to why light is so useful for astronomers. Well, one of the main things, especially in early modern physics, is something which Max Planck described and laid the foundation for quantum mechanics. That is basically the relationship between the frequency of something and its energy. And this became particularly useful because it allowed basically scientists and physicists to create a relationship between the wavelength of a given particle of light, so a given photon of light, and its energy. And it is an inverse relationship. So the smaller the wavelength of light, the more energetic it is. And basically this means that, for example, the reason why you have blue skies, like why the sky is blue basically during the day, is because the sun is bombarding us with white light, which basically encapsulates all of the colors of the rainbow. And basically the very energetic photons, so the bluer wavelengths of light, are the ones that are scattered the most, like in our atmosphere. Like they're the ones that bump into the molecules in our atmosphere, and they scatter the most basically due to a phenomenon known as Rayleigh scattering. Besides the relationship between the wavelength of a photon and its corresponding energy, there's also basically the fact that stars themselves, like our sun, actually runs on a process known as nuclear fusion, where you have smaller nuclei basically fusing to become a larger thing, basically like transmutation, like actual alchemy transmutation, but not alchemy, but actual science. So you typically have in stars, in a very simplified manner, which I try to explain it here, you have two hydrogen isotopes. You have deuterium, which is like H3, so one proton and two neutrons, and you have tritium, which is one proton and one neutron, if I'm not mistaken. So you have these two isotopes of hydrogen floating about in space, like basically as interstellar dust, and as they clump together, and at some point they clump together so much that they enter a point at which they are in something known as Jeans instability, which is just jargon for saying that they have such a high amount of mass at such a dense amount of region that these atoms are going to start fusing with each other. You have that, for example, in hydrogen, it's basically just one proton. So you have two protons which come so close together that they overcome something known as the Coulomb barrier. And the Coulomb barrier is basically just a fancy way of saying that they overcome their electrostatic repulsion. So instead of the plus charges repelling each other, they're actually able to snap together and basically form a new nuclei. So basically form a nucleus of a helium atom, and usually helium-4, so an alpha particle. So in this process, you have a lot of energy from both of these like two hydrogen isotopes before they fuse into helium and they release a neutron, which is typically an indicator for fusion. They release occasionally also things like an anti-electron neutrino and also a lot of energy, and energy in the form of heat as well as energy in the form of light. All of these like constituent extra particles are due to needing the conservation of energy, and especially like Einstein's equation of E equals mc squared. Basically, this tells us that you have light being produced from this fusion process, and this is basically the thing that powers like stars. Now that we know that basically what powers stars, as well as the relationship between the energy of a photon and its wavelength, we want to look at one final piece of the puzzle, and that is basically that rays of light coming from a particular source, let's say a spherical, like a ball shaped source, such as a star, as it's very decently approximated to be like a ball. The amount of light basically that can come from this spherical source can vary in intensity. Like the more intense the amount of light coming from this, the higher something known as its flux is. So basically, if you were to imagine a bunch of rays of light coming from this spherical thing, well, the higher the intensity, the more rays of light you have sticking out of this spherical object. And the lower the intensity, the less of this. Astronomers typically are very much interested at studying basically the flux of light coming from stars out there, basically out there in the sky, basically that you can see with your naked eye or with your telescope. So they point their telescopes, both Earth-based and like the space-like based telescopes, and they try to measure the flux of this star over given ranges of wavelengths, as this can give them something known as a black body curve. So you have this very fancy and weird looking curve which kind of shows you basically what the flux of the light being emitted from the star is at a given wavelength of light. And you might see all of these weird dips and such where like light is being absorbed by a particular element or something due to like dust or something along those lines. And in principle, astronomers want to look at the total flux of the star, as this can give you a lot of useful information. And this total flux, also known as the bolometric flux of the star, is actually very hard to attain in practice, because either you want to have a very long exposure times to like that one particular star, which I mean that's very impractical, or you want to have very sensitive like apparatus and devices, which I mean that's kind of what James Webb Telescope is doing on the infrared end of things. But still, so astronomers and especially the instrumentalist ones and engineers were clever enough to come up with a solution to this, and that is the use of filters. So by actually looking at less light, you tend to see things in more detail, which might sound counterintuitive. But the way this logic works is basically if you have a filter which blocks out all other wavelengths of light, with the exception of a particular given wavelength of light, such as the blue like wavelengths of light, or the ultraviolet wavelengths of light, or some of the other visible wavelengths of light, you can very accurately like get an image for your given object at those wavelengths of light. And by combining those together, then you can have a nice image of your whole astronomical object and still somewhat mimic that black body like data that you wanted in the first place. This technique is really cool. It allows you to get something known as the apparent magnitude of your star or of your like celestial object at various filters, and in general this can be used to obtain like an overall apparent magnitude of the object you're interested in. And because of a relationship that exists between the apparent magnitude and something else known as the absolute magnitude, as well as the distance to the astronomical object, then using the apparent magnitude and the distance, which astronomers again can very cleverly figure out the distance to interstellar object, not by sending a rocket to them, because a lot of these things are light years or even parsecs away from us, but they use clever techniques from the cosmic ladder, such as parallax or using standard candles and such for very far away stuff. And in that sense, you can still determine distances to things in space. So if if you have the distance to your star and as well as the apparent like magnitude, then you can figure out the absolute magnitude. And the absolute magnitude is basically the magnitude which the star would have at a distance of 10 parsecs. And parsecs, basically very similar to light years, is a unit of distance, but only it is much larger than light years, so you can imagine that some of these things are very, very far. But the reason why you do this is because if you, for example, want to look at a sample of many different stars and see how their brightness basically varies and their luminosities vary, then you can create this plot basically looking at these various stars if you were to pretend that they were all at the same distance away from you. And this is very useful because looking at how bright basically these stars are can tell you things such as the size of the star. Like a star that is relatively big in size is going to have a larger absolute magnitude, so it tells you something about the actual size and diameter of the star, as well as the color of the star. And the color of the star can tell you something about, in essence, the effective temperature of the star, due to something known as Wien's displacement law, which basically describes a relationship between the wavelength you observe and the temperature of the given object. So if you have an absolute magnitude of a star, you can actually somewhat extrapolate what its temperature would be just by using like thermodynamics. So this is incredibly fascinating, and not only for studying like stars, but also for studying things out there in the far depths of space, for example, with some of the many objects you can have in interstellar dust, as well as objects that lie, for example, in the accretion disk of like black holes and such. But on top of that, there is a second cool use of this whole filtering technique, and that ties into my original like thing which I talked about with like filters and images not really looking like you see them online with like the pictures of the James Webb Telescope. And that is basically that different filters basically allows you to look at astronomical objects with different like amount of details and precision. So for example, if you're pointing your telescope at a galaxy like the Andromeda galaxy, if you're looking at it in the visible like spectrum of light, then you'd see something like this. It looks like this grayish blob, and you cannot really make up all of the fine details because, well, there are a bunch of, well, white light basically from all of those stars in that region being sent to you. So you cannot make out finer details like the spiral arms of the galaxy and things like that. But if you were to use different filters, like for example, astrophotographers are commonly use things like the hydrogen alpha, the O3, and the S2 like filters, narrowband filters. Well, all of these names basically relate to some isotope of some of these atoms like hydrogen, oxygen, and sulfur. You filter out basically only the emission line that you get for one of these like isotopes, so from hydrogen alpha, O3, or S2, and basically you take pictures of, for example, the Andromeda galaxy, or for example of the Orion nebula in hydrogen alpha, in O3, and in maybe S2, but sometimes it is not used, maybe sometimes just hydrogen alpha, O3, and some other use of O and H are used. And then basically you get all of these various images which show you, for example, in one of them you see the white dwarf in a given nebula. So if you have, like, for example, the Ring Nebula, you can see the white dwarf in one of these filters much better than the other, because in the other maybe you have the dust is blocking the light. And in essence, by combining all of these together and kind of exaggerating the color scheme a bit, you can get what at the end of the day looks like these gorgeous pictures which you see. And that is really cool. And not just for, of course, creating these beautiful pictures and making people aware of like space and the science that is done, but also because it allows you to study these objects and look behind. For example, if you're studying galaxies, it allows you to look behind all of the interstellar dust, for example. And if you're purely interested in some of the OB stars, so OB is just jargon for some of the young hot stars which are very blue, then you can use some filters, like for example the blue filter or the U filter, which is the UV filter, to look at basically these young hot stars. If you want to look at older stars, you use something like the red filter or the eye filter, which is for infrared. So all in all, this usage of filter is actually pretty damn crucial, and there's so much that you can dive into this, and I highly encourage you, if you're curious about astronomy and maybe even just astrophotography, to look into this concept of filters, as I find it one of the many fascinating uses of light in astronomy to study faraway objects. It's insane that one can basically study like objects that lie millions, billions, and unimaginably far, like amounts of like kilometers away from us, just by looking basically at the light which we receive from them. So that's really cool. I hope you guys found this video educational and interesting, and I hope that it was somewhat of a quick paced video, as I just wanted to do a cool little video as to like some cool applications of like astronomy. I hope to see you guys very soon, and I hope you guys have a great like New Year's Eve, and of course like rest of the holidays, like if you're like having a holiday. I hope to see you guys very soon again in a future video, and bye.